Well, good afternoon, everybody. My apologies on the mistake I made on the scheduling of this. I really meant for it to be today at 1 o'clock, on Thursday at 1 o'clock rather than Tuesday. But I did a cut and paste from last week's announcement, and you can see some stuff sort of held over that I didn't change. So tried to save myself some typing and end up sort of screwing things up a little bit. So my apologies on that. I hope there are some folks that are watching. If you are watching, even if you don't have a question, just give me a little bit of a hello so I know that there are folks that are here. My viewers that shows up on my stream dashboard here isn't necessarily perfectly accurate, but if there are folks with questions, please ask them as we go. I'm going to be talking a little bit about the lecture notes that I posted up this week, just so in case there aren't folks that actually watch the live stream, that you can watch it afterwards, after the fact, and get some information from it, even if there aren't any any questions or folks that had a chance to to watch it on their own here live. So overall, I got finished grading the exam. Overall, it looked like it went pretty well. Hey, Sam, good to see you. Glad you could make it on such short notice. The exam, I think it went pretty well. There were some folks who went over the time limit a little bit or something like that, and I know it might have told you got a 0 or something like that. You didn't. I took that out of there. So as long as you're within a couple of minutes or relatively close to having your getting it in on time, you're good. There's a little bit of a grace period in there that I'm willing to be flexible on. I get that. Sometimes you're fighting the computer and it just doesn't work out like you'd hoped and all that. So so no worries about that. Everybody got a grade that was looking at and finishing out the exam. And overall, I thought it looked like it went pretty well. That was good. It didn't seem like folks had too much trouble, but there were a couple of times when folks were entering their calculational style examples and stuff like that. And they fought a little bit with the equation, the equation editor or something like that. Just make note that just type in that you were having a little bit of trouble with that, and it should go. Sam's asking the question: when you will put exam 2 in the grade book? Oh, exam 2 isn't in the grade book. Shoot, I hadn't thought about that. Thanks for reminding me about that. I haven't been into my office in a couple of weeks now, just because they're asking us to limit our time in there. But I'll go in and check. I think I'll go in tomorrow then and see. I forgot that I hadn't put exam 2 in, so sorry about that. So yeah, I'll make sure that that's in there and available. Exam 3, the one that you just did online here, that should have been exported already. I just got that done a little bit ago. So sorry about that exam 2 was it's taken so long to get in there, but like I said, just slipped my mind, and I'll get it in there and make sure that it's available so you can see. Like I said, if you have questions, don't wait for me to get to it. Just ask your questions now on stuff, on the techniques. I'm going to start talking about, because of the delay, I'll just start talking about stuff, and as questions roll in, I'll answer them. It doesn't even have to be related specifically to the topic we're talking about. I'll just make sure that things get answered. So, about where we're headed this week and all that stuff. So the way we're headed now is we're going into practical electricity and magnetism. We're starting to get towards circuit ideas. So up until this point, up until the end of last week, we'd been talking about, okay, what's the electric field like? What's electric flux? What's the definition of voltage? It turns out it's going to be more, it's more practical later on, but what's the definition of the voltage? And how's it related to electrical potential energy and all those sorts of things? So we had the real, the basic theoretical understanding of how charges interact, and now this week we're starting to talk about devices that make use of this stuff, and we're going to get more practical. So now that we've talked about voltage, we've established those things, we start with capacitors. And the way we're making our way through this is we're going to start with the idea that charges don't move. That's the concept. Well, I mean that they do, but we're going to be looking at them while they're static, while they're unmoving. So we're talking about a situation where we've got this capacitor that's going to be able to be charged up, that you can attach it to a battery and then charge for a brief time, will flow off of the battery, deposit itself on the capacitor, and then once the capacitor is charged up, the charge sits there, separated by some, non-conducting, insulating, either material or a vacuum or something like that. So I'm going to make use of circuit symbols starting now, and I'll just outline what that is, because that's something I guess it's usually something I talk about in lecture, but it may not be clear what these circuit symbols are, so let's make them as clear as possible. So first of all, a wire is just going to be a line, right? Oops, we're going to need a brush. A wire is a line in a circuit diagram represents a resistanceless wire, a wire that is a perfectly good conductor and travels through. So a wire is just a line. A battery, the symbol for a battery is two parallel lines. And then this is sort of the wire. So these are like the terminals of the battery. A battery then is a device that maintains a constant potential difference between its terminals. So an example of like a 9-volt battery or something like that. Or let's say we're talking about a real simple one, like a little AA or AAA battery. On one terminal of the battery, the top of the battery is a positive, and the bottom of the battery is negative. And if you would take a voltmeter and touch each end, you would see that it measures 1.5 volts. And so it's a 1.5 volt battery. There's a chemical reaction that goes on inside of the battery that maintains the potential difference between the top and the bottom terminal at about 1.5 volts. The healthier the battery, the more able it's able to, the greater ability it has to maintain that voltage at a nice steady value of 1.5. As the battery gets older and the electrolyte gets, the chemical reactants inside get used up, then the battery has a hard time maintaining that voltage, and we were talking about voltage, the battery dying then. But the idea, though, is that the battery is represented by these two parallel lines right here, and then the wire that comes off of them can be attached to some other device or something like that. So this is what a battery looks like in a circuit. There's a circuit symbol. And the positive terminal of the battery is the longer parallel line, and the negative terminal of the battery is the shorter one. So this is at a higher potential than this. So that's how that works. A capacitor, the symbol for a capacitor is two parallel lines that are exactly the same length. In some capacitors that have a polar nature to them, one of them might be curved, but I'm not going to draw it like that. So here's like the wires attached to the capacitor. There's one and the other. So if I was going to draw a circuit where I had a battery connected to a capacitor, I would draw the battery. Then I would draw a wire that goes over to one part of the capacitor. So I'll just have the capacitor right there. Here it is. Two parallel lines of equal length. And I would finish out with another line that connects to the negative terminal of the battery. And this would be the circuit that involves a battery charging up a capacitor. So I've given you the symbols now. And if there are questions on that, please type in the chat. But what is a capacitor? I talked about what a battery is. It's a voltage source. But what is a capacitor? Capacitor is a device that stores charge. And it's defined by the capacitance. So really what it does is the actual charge in the capacitor is how much charge ends up getting stored on, how much positive charge gets stored in the positive plate. What always happens with the capacitor when it's fully charged is the capacitor will have positive charge coming from the positive terminal of the battery, will end up on one side of the capacitor, so it'll have plus Q on that side, and then it always has negative Q on the opposite plate of the capacitor, the opposite part of the capacitor. So a capacitor is basically a pair of conductors arranged geometrically some way and separated by some insulating material, either an insulator itself or the vacuum that does, empty space, which doesn't allow the charges to the positive charges just zip over here and neutralize with the negative charges. So it's just a device that separates charge. It's a really simple device. It's just a conductor, pair of conductors that charge can sit on, and then they're separated by some distance. And that's it. That's all a capacitor really is. It has lots of uses, it turns out. just that really simple device. But we'll talk about the applications maybe a little bit later once we've started talking about current stuff like that in the next chapter, which we get to at the end of this week as well. So this is what a capacitor is, and this is a circuit then which is able to charge a capacitor. So when we say that the capacitor has some charge on it, the actual total charge on it is 0 because there's plus Q on one plate and there's negative Q on the other plate. But we basically define the charge on the capacitor as whatever charge on the positive plate. So it turns out that for a capacitor like this, we say that the charge that fits on the positive plate can be expressed. It depends on a couple of things. First of all, it's going to depend on the voltage that you apply to it. If the higher the voltage, the more charge actually will sit on your positive plate. The more charge will end up on the capacitor. The bigger positive Q it will be, and the more negative Q will be. So it depends on the voltage. And it turns out that if you double the voltage, you'll double the amount of charge on the capacitor. So if I go from, a 1.5 volt battery to two 1.5 volt batteries stuck together in a way so that they produce an overall voltage of 3 volts, which is what happens when you put them right after one another. The total voltage across the positive terminal of the top battery and the negative terminal of the bottom battery is 3 volts. Well, if you double that voltage that's applied to the capacitor, you'll double the amount of charge that's on that particular capacitor. So the charge on a capacitor always is directly proportional to the voltage that is applied to it. But it also depends on something else. It doesn't just equal that. There's actually a quantity called the capacitance, C, which is a measure of the geometric and electrical properties of this device, whatever it is. Maybe it's a parallel plate, maybe it's some other geometry, but the size and the shape and the electrical properties of that device determine how much charge will sit on it for a given voltage. And all of that stuff, all of those electromagnetic and geometric properties are summarized by assigning a number to it called the capacitance. So this is the capacitance. All right. So capacitors have capacitance. And it's a number that we assign to how much, all the geometric and electromagnetic properties that allow it to store charge. So there's the capacitance. So the charge is always that sits on the capacitor is always proportional to the capacitance. The more capacitance it has, the more capacity it has to store charge. And the bigger the voltage for a given capacitance, the more charge you'll get. So that's the definition of the capacitance. Now, hopefully this is useful information, or maybe you've already seen it, maybe it's clear. If this is boring to you, just say, I got no questions on this. This is, I don't need to see this. Can you tell me more about whatever you want to know about? I guess I'd rather you tell me what was unclear in the lecture notes that you've seen so far, so that I can address those rather than go over stuff that you already get. But this is the definition of capacitance. What happens, though, is one capacitor is, when we get into future stuff. I should mention one other thing. If you put a bunch of charges next to one another, that takes energy. You got to do work to force those all those positive charges to be all close to one another. And all the negative charges here, if I put one negative charge there, another one, the more negative charges I put there, the more charge gets stored, the more work it takes to actually put those charges there next to one another. You got all these positive charges next to all these other positive charges. That takes a lot of effort. So it turns out that there's an electrical potential energy associated with all the charge that sits on the capacitor. And it comes from the amount of work that the battery must do in assembling that distribution of charges, where there's a whole bunch of charges here and a whole bunch positive charges there and a whole bunch of negative charges there. So it turns out that this can be calculated from 1/2 CV squared, but there's two other versions of this formula which also arise from the fact that I could put it in terms of the amount of charge that's stored, or I can put it in charge. I can eliminate the capacitance in terms of the charge, or I can eliminate the voltage in terms of Q and C. So there's two other versions of this formula that show up. 1/2 CV squared is one of them. The other one is, let's see if I can get this right. So Q is equal to C over V. So if I put that in here, C is equal to Q over V. So that looks like the other version would be 1/2 Q is equal to C over V, or that C is equal to Q over V, then I have 1/2 Q times V is another version. And another version is 1/2 V is equal to Q over C, so that'd be Q squared over C. So these are the three versions that you can get for the amount of electrical potential energy. This one's if you don't know the charge, but you know the capacitance and the voltage. This one's if you know the charge and the voltage, but you don't know the capacitance. This version is if you don't know the voltage, but you know the charge and the capacitance. That's that. Yeah, Sam's asking about if I can go over electric dipoles and dielectrics. Yes, I sure can. I've got a, let me see here. Oh, I had a separate thing here. Let me have a look here. All right, so let me do this. I'm going to copy something from. All right, so let's let me do a little copy and paste here, maybe. I'm going to paste this little situation here. That's not awesome. Let me see. Let me cut that. See if I can find a better picture here of the situation. Electric dipole in a field. Yeah, maybe this is better. Yeah, this one will be better. This one will work better. Okay, just so I don't have to draw it, there's a decent, there's a decent image of that here. So let's paste it here. Oops, that's a little big. All right, let's just, all right, so it's a little distorted, but hopefully you get a sense of what this picture is. I'm going to make it so it's a little bit easier to see. All right, so I don't like the way that looks now. Let's get rid of it. See if we can. I'm going to paste it again. See if we can get it better. Okay, so let's just look at the picture that I'm showing here now of an electric dipole in a field. So this is the idea of a dipole. The idea of a dipole is real simple. It's just I've got a positive and a negative charge separated by some fixed distance, which they're going to call R sub s. I call D in the notes. So this is what an electric dipole is. Now, notice that an electric dipole has positive and negative charges. They're equal amounts of charge, but just opposite. And think of these as like little dumbbells of charge, where one end of the dumbbell is plus and the other dumbbell is the other end of the dumbbell is negative. Now, if I put this in an electric field, so there's an external electric field that this dipole is experiencing. The force so it's showing that here as the electric field pointing straight towards the top of my screen up here. It's pointing that way. You can see here's the electric field vectors at these different spots. Okay, the positive charge, it feels a force in the direction of the electric field. The negative charge feels a force opposite the direction of the electric field. Remember, F is equal to Q times E. So this little dipole, this electric dipole, is going to experience not a net force, because the amounts of the forces, as long as it's a uniform field, the amounts of the forces are equal in magnitude but opposite directions. So what it's going to do is it's going to experience a torque. So it's going to tend to spin this thing around this axis. And that's going to tend to make the electric dipole, which is originally like this, it's going to twist it around so that the dipole moment, which is a vector which points from the negative charge towards the positive charge, it's going to rotate that around to align it with the electric field. So there's a torque that acts on every electric dipole. Now, what does that have to do with the capacitor? Well, it has to do with something that we call dielectrics. A dielectric is a material that is made up of a whole bunch of little dipoles. And in fact, practically everything around you, in some sense, at least if it's an insulator, is a dielectric. It is a whole bunch of molecules and atoms that act like little dumbbells of charge, like I've shown on the screen here. Equal amounts of charge separated by a fixed distance. That if you put them in an electric field, they're going to want to twist and align with the field. Now, the thing about what happens when that twisting occurs is that the external electric field and the field due to the dipole itself, the total field is going to be the sum of those two. And those are actually in opposite directions. The dipole field points opposite the direction of the electric field, and it tends to weaken the overall electric field inside the dielectric. So the way I'm going to get rid of this now, hopefully this is relatively clear, but I'm going to delete my little selected area now. And now I want you to imagine a situation where I'm going to select here, I'm going to clear the space. I want you to consider a situation where I've got a parallel plate capacitor. And I've got, oops, they're supposed to be parallel. There we go. All right. So this one here is the positive plate. It's got all the positive charges, and this one's got all the negative charges on it. Which means, in this case, I'm going to just draw it here. I've got an electric field vector which points away from the positive charges towards the negative charges. That's the direction of the electric field vector. All right. Now what I want you to imagine is, okay, we've got the charge on the plates here, and it's a certain amount. Let's say I've got plus Q up here, and it's distributed uniformly over the top plate. And then I got minus Q on the bottom plate, and it's distributed uniformly over the bottom plate. And let's say there's empty space in here, so E is whatever E is. So this is the field due to the charges on the plate. Now I want you to imagine a situation where I'm going to take that space between the two plates. I'm going to fill it with, I'm going to leave a little bit of space, but this is supposed to be a solid dielectric material that is made up of little dipoles, so little arrows. Okay, so this is the little dipole moment due to one of those little dumbbells of charge. Now, if these charges weren't here, that dipole could be in any direction. So the electric field due to those dipoles would be zero. But now imagine I do have this little dipole in here, and it's feeling the effects of the field due to the charges on the plates. What's that going to do? That's going to make this little dipole want to align with the field. It wants to go this way. And notice that this is where the positive charge is going to be. So I'll say here's where the little positive charge on the dipole will be, and this end over here would be where the negative charge would be. Now I want you to tell me, so this is the dipole moment, which we call P. What's the field? The electric field due to the dipole. So it's going to be the electric field due to this dipole. Okay, well, this is the dipole moment is this. The electric field due to the dipole moment, notice it points away from positive charges and towards negative charges. In this region right here, the electric field due to the dipole points up. The electric field due to the dipole points up. And notice if I say, well, what's the total field in that region where that little dipole lives? What's the total electric field, not only due to these external charges here, but also due to the internal charges in the dielectric? Add those two fields up. Well, one of them, the external field, points down. The one due to the dipole points up. They at least partially cancel. The dipole is little, so it doesn't have a huge field, but it has a small. But it tends to at least partially cancel the electric field in this region here where the dipole lives, and that's true for all the dipoles that live throughout the entire dielectric insulating material that's here. So what does that mean? It means that the overall total field inside this material is smaller than the original external field due to the charges on the capacitor. So I'm going to call that EQ, the electric field due to the charges on the capacitor. Okay, now, is that clear? Does that make sense? The dipole field is partially canceling the external field due to the charges on the capacitor. I'll pause a little bit and see if that's going to go, but let me know if you're following along. If you have a question on that, let me know in the comments. I'm going to continue briefly, but keep an eye on the comments in case there's something, because I don't want to waste time here if something's clear. Remember how you calculate capacitance. I talked about this early on in the lecture notes. The way that you calculate capacitance is you put a certain amount of charge on your conductors, on your capacitor. So this one, it's got Q on it already. And then you say, all right, let's calculate the difference in voltage between one plate and the next. using negative E dot ds. And then use the definition Q is equal to CV. This delta V here is the voltage difference between the plates of the capacitor that we just calculated. And this would then imply that the capacitance that we can calculate is equal to Q, the charge that we placed on one end of the capacitor, divided by the voltage that's produced when I put them there. Okay, so here's what's going on. Like I said, we placed plus Q on this capacitor. We're not attaching it to a battery. Let's say we've just charged it up. We placed, with an eyedropper or a tweezers or whatever. We put a bunch of charge on there, and we put negative Q on the other side. And now then we put a dielectric inside of here. Now, if the dielectric isn't there, when I do E dot ds, this isn't just this is the total electric field. It's always the total E dot ds that you have here. So if I go from here to here, this is a uniform field. I've got the electric field dotted into ds, and there's going to be some voltage difference. And since it's between two parallel plates, uniform field, so it's just E times the separation. Okay, simple, what the voltage is. But it takes into account what the electric field is. Now, if I place the dielectric in there, the field is smaller. Which means if I got the same separation, so I haven't changed how far apart the plates separated, when I take this out, E is just a constant, so it comes out of this. This would be delta V is equal to negative E times the separation of the plates. But E is smaller now. And since L is the same, separation is the same, delta V is going to be littler. Which means now, notice what happens here. I still have the same amount of charge on the plates as I had before. I still put plus Q up there, but with the dielectric inside there, the voltage is less. What does that mean? It means the capacitance went up. So by placing a dielectric in between the plates of the capacitor, I enhance the capacitance by some factor. And the factor by which the capacitance increases is the same factor by which the electric field decreases due to the presence of the dielectrics, the dipoles inside of the dielectric. What we call that factor by which the electric field gets reduced, we call that the dielectric constant. It is a dimensionless constant. So let's say the electric field, when I put the dipole, the dielectric material in here, let's say that I notice the electric field goes down by a factor of, goes down by a factor of 2. So the electric field's half as big as it was before. Dielectric constant then would be 2. And that would mean that the capacitance is doubled because the voltage is only half as big and I've got the same amount of charge. Okay, does that make sense? So the dielectric constant we call kappa. It's kind of look like K, but I'm trying to put a little, that's kappa. This is the dielectric constant. The electric field is equal to, the resulting overall electric field is equal to the external field divided by kappa. And then, but the capacitance then increases by the factor by which the electric field is decreased. So I'm going to call this C0. The capacitance when there is empty space between the plates of the capacitor. If I put a dielectric with a dielectric constant of kappa, then the new capacitance is kappa times C sub 0. So it's just a factor. Kappa is just a factor called the dielectric constant, and it's a dimensionless number. Does that answer what you were asking about? It seems like that. I'm trying to anticipate what you really wanted to know about from that, but I think that covers it. Can you let me know, Sam, if that's enough, or do you want to see more, or that's good? Okay. So that's the nice thing about dielectrics. They make capacitors better compared to empty space. So if you decide you want to be an electrical engineer and you say, well, I'm going to go into the business of designing a better capacitor, you would want to be searching for a material that has as much dielectric constant as possible, because then you could make a capacitor with all really, really big capacitance. Okay, are there any other questions that I can answer about stuff? That was sort of the lecture notes for, I think it's for Wednesday or something like that? Does anybody have a chance to look at the lecture notes on current, which were today and tomorrow's notes? Ostensibly they are. Of course, you can look at them at any time you want, but I'll just pause for a little bit here because I had another live stream this morning for my 1020 crew, and I'm a little hoarse because that went a little over an hour as well. So, yes, I can go over the variables for the current and resistance notes. I'm going to erase this then so we give ourselves a little bit of space on stuff. And talk about those a little bit. Normally, under our normal circumstances with how I would teach current and resistance and stuff like that, I would go into a little bit of more detail in class about the Drude model, just because it's kind of hard to explain, and we're sort of in emergency mode here, with our being online and stuff like that. I'm not going to put a lot of emphasis on that. That's one thing that we're going to have to just let be a little bit, maybe it's not awesome, but hopefully it's good enough. Let's see. So, let's see. I'm looking at the notes probably for today's. I'm gonna look at those first. Let's see. Maybe what you're talking about here is you're probably talking about, I'm going to guess, that you're talking about the idea that that might be a little confusing, that, current, oops, come on now, let me write. All right, here we go. I is equal to, the current is equal to N times Q times this, what we call the drift velocity, times A. In a particular, it's supposed to be a D there. Okay, maybe something like that. I'm guessing that that's probably because I know there's a lot of variables in there, and like in a live class, I would of course be telling you what each one of those is, and of course it's probably not particularly clear in the lecture notes without some further explanation. If that's not what you want, if you want something else, just let me know right now in the lecture notes, Sam, and I'll fix it. So having a look here, let's see what I'm talking about here. So the situation is this. We're saying we've got a section of wire, so I'm going to draw sort of a cylindrical section of wire. And there's charge which is flowing through the wire. Okay. So, here, alright, thanks, Sammy. Let's see what we got here. Okay. So this is a cylindrical wire that's really typical of a type of wire that you might see in real life. Of course, it has a particular cross-sectional area which is circular. So it has a circular cross-sectional area. If I'm looking straight at the the wired edge on or something like that, I would see a circle. That's the area we're talking about here. Whoops, I didn't mean to click there. Okay. All right. So that's the area there. The A that's right there refers to the cross-sectional area of this. Now we get to some microscopic quantities here. The N that we're talking about is the number of charge carriers per unit volume in that particular material. So if this is copper, okay, let's say this is a copper wire, then N would be some number which told you, well, how many electrons are free to move around inside of the copper because it's a conductor. And obviously a conductor is going to have a relatively high number of these charge carriers per unit volume. So it's like, how many free electrons are there per cubic meter of stuff for copper? For aluminum, it might be something different. For, for silver, it's something else. Every conductor has its own number of charge carriers per unit volume that are free to actually move within the substance. Q is the charge on each charge carrier. Most of these are electrons, so this would just be that 1.6 times 10 to the minus 19 coulombs. We don't worry about the minus sign here because that refers to the direction. Or that's concerned about the direction, but this is just talking about the magnitude of the current. V sub d is what we call the drift velocity. So electrons, when they move through a substance here, they don't simply move in a straight line because it's microscopic. If I got a little electron, it travels around here. It might run into an atom on its way and might get scattered back, and it's going to move sort of in random directions here as it wanders its way down. Notice that I'm generally moving to the right on my screen at least. But the electron during this time is sort of wandering around as it runs into atoms at various points. So when its average velocity, as it's sort of overall in the average sense drifts down, it is what we're talking about here. It's sort of the average velocity of this thing traveling from left to right so that the current flows from left to right. So that's what we mean by the drift velocity. The instantaneous velocity of the electron could be it can be millions of meters per second. But it's doing this. It's zipping around, but on average, it's drifting down. It's down the wire. So that's what each of those individual terms means, and this is sort of the basis of the Drude model of conduction, which is not a terribly important concept, but I wanted you to understand at least a little bit about what current is and all the factors that go into it. The bigger the wire, the bigger the area, the larger the current, because you're just going to capture more charge carriers. There's going to be more charge carriers more electrons to actually carry current, the thicker the wire is. So all of these, and if I have a better conductor, I have more charge carriers per unit volume. If the density of the number of collisions that happen is low, then the drift velocity will be bigger, and instead of drifting really slowly down, if they maybe drift a little bit more quickly down, then you'll get more current as well, because charges will generally move almost straight from left to right rather than wander around so much. So that's the factors that go into determining current on a microscopic level. When you use an ammeter, it doesn't care about all these little details. It just says, well, how much charge per unit time is traveling through this wire. So it's like if you put like a little charge detector at the end of this wire, and you said, okay, anytime a charge pops out, it tells me how much charge just left, just went out the end of the wire into the next section of wire. And then you use a stopwatch. All the ammeter is doing is telling me how many coulombs of charge each second are exiting the wire. Of course, there's charge going into the wire from this end too, but if you look at just like what is the number that passed through this one per unit time, that would be the current. And it's measured in coulombs per second, which is also known as an ampere. Is that enough, or did you want a little bit more? Or you can even tell me if it's too much, because then I know when to shush. And let you ask more questions. But please do continue to ask questions if you got them. Totally interested in seeing what you got to say here and what you'd like to know a little bit more about. Okay. Anything else from folks that you want to know about? So this is your basic idea of current. It turns out that Ohm's law is an important idea that's also related to current. And Ohm's law basically says if I have this section of wire like this, if I have a section of wire and I apply a voltage to the wire, so for instance, if I did something like this, let's say I attach my wire to a battery. Look at that, I'm using my my symbols. Well, kind of. That's not the best. I have to make it better because it's a terrible battery symbol. I can do better, and I will. Okay. There we go. All right, so there's my battery, and I attach it via wires, resistanceless wires, to this device. Then what I find is that the voltage and the current are directly related to one another. And what I find is that I get that this is equal to the current that is produced times rho times L over A. Now A is that cross-sectional area that we have here again. And rho is the resistivity of the material that this is made out of. So we define then, we say V is equal to I times R. This is Ohm's law to an extent, where R is all of the stuff that I'm putting in parentheses right now. It's resistivity times the length of this thing divided by the cross-sectional area of the wire that we're talking about. So resistance and resistivity, they sound similar. They got a lot in common, but they are not the same thing. Resistivity is a material property. So like copper has a different resistivity compared to aluminum, compared to steel, compared to gold, compared to platinum. All different conductors have different resistivities. And in fact, insulators have resistivity too. It's just that their resistivity is really, really big. The resistivity of really good conductors is on the order of 10 to the minus 8 is the number we assign to it. The resistivity of insulators is like 10 to the positive 10th, so it's a huge difference in resistivity. But it's a material property. The resistance depends on the material via the resistivity. Oops, that should be rho, the resistivity of the substance, which the resistor is being made out of. There we go. But it also depends on the geometry of the resistor. It has to do with the longer the resistor, the more resistance it has. The smaller the cross-sectional area, the bigger the resistance it has. So the resistance actually tells you how much current you'll get for a given voltage. This implication here is that the current that results from a given voltage being applied to a resistor is equal to V over R. It's a cause-effect relationship. The voltage causes the current, but it also depends on the properties of the object that I'm trying to make the current flow through. The more resistance it has, the less current will flow. And how much resistance a particular device has depends on what it's made out of and what the shape of the object is. There's a lot of parallels between the idea of resistance and the idea of capacitance. Because capacitance, as you recall, what we talked about earlier in the week, haven't talked about it in what we're talking about now, but the capacitance depends on the geometry of the capacitor, its size and its shape, the area of its plates, the separation, all that sort of stuff, and it also depends on the electromagnetic properties of the dielectric between the plates. Okay, so it depends on geometry and electromagnetic properties. Resistance, same thing. It depends on geometry, the length and the area, and also depends on the electromagnetic properties of the material that it's made out of. In that case, the resistivity. So this is Ohm's law. We can calculate the resistance of a particular device using this expression here. But once we know the resistance of that device, which depends on its geometry and its electromagnetic properties, for a given voltage, I can figure out how much current once I know that resistance. Any questions on this that you can think of? I know we're about 45 minutes in, and hopefully I'm answering the questions that folks want to see. If you have specific questions on homework or stuff like that, please bring those up now too as well. That can be totally helpful to other folks that haven't had a chance to look at the stream. Anything else you want to see? Combinations of capacitors, we haven't talked about that yet. So I'll just pause and let my voice rest a little bit, and then see if folks have a question that I can answer about it. And I guess while I'm paused here, I'll just interject a little thing. I guess I mentioned on the schedule on Monday that I posted on Monday that something about a test, an exam. that was just a holdover from last week. I didn't realize that was still in there. Like I said, I cut and pasted into that. There's no exam coming up this week or next week, obviously. There's really no way. We just started a new unit. We've got this chapter on capacitors, which we dealt with pretty quickly. We've got the chapter on current and resistance that we still have to finish. And then there's still yet another chapter after that. The chapter, I can't remember which ones it is. I think it's 24, 25, 26, 25, 26, 27, something like that. But we got another chapter that actually deals with electric circuits and resistors and Kirchhoff's rules and all that sort of stuff. So we have time yet before the next exam. Hopefully that wasn't too jarring to folks to see that. It's like, what? There's an exam on what are we doing? One chapter per unit now? But now we're going to do 3 like usual. These 3 go together. They're all sort of the circuits thing, and then we'll, and it's really the meat of what a lot of folks need to know about for circuits in your engineering program if you're going that route. So this unit is probably really important for all that sort of stuff. Anything else that folks want to know about? I'll just pause, like I said, my voice rests a little bit. Okay. Anyone else have any questions besides Sammy? Okay. The one topic that I didn't really discuss live on this thing yet is combinations of capacitors. I'm going to give a little brief exposition on that just so that everybody has a chance to maybe see and hear about that. And just to sort of fill out, please ask questions though in the chat. If you still have some, feel free to do that. I'll talk a little bit about those. And then you sort of finish that up here over the next, 12 minutes or whatever we have left. So the idea of combining capacitors is it's asking ourselves, if I attach, say, 2 capacitors, one right after the other, that's what series means. So this is a simple circuit with a pair of capacitors in it, and they are attached to a battery. Okay, here's our battery. I just want to make sure we got our battery there. That's clear what that is. Okay, and this is capacitor number 1. This is capacitor number 2. Well, I'll just leave it. All right. And it's attached to a battery that has a voltage V, and we're not sure what that is. And this is what we call a series connection. The reason it's called series is because the capacitors come one right after the other, as they're wired in such a way as to go one right after the other. So that's a series. The question is, can I find a situation where I can replace those 2 capacitors with a single capacitance, with a single capacitor that does the exact same thing, that has the same exact effect on the battery? So that's equivalent capacitance. So what that would mean is that I take these 2, replace it by this 1, and it would still pull the exact same charge off of the battery. So let's say I have these 2 here, and some certain amount of charge gets pulled out the battery, Q, and then I just say, well, I've got Q on this. Maybe if I have a 9-volt battery and I pull 1.5 microcoulombs total off the battery, and it ends up distributed on these capacitors somehow, some way. Then I would want to say, well, how much capacitance, what capacitance would a single capacitor have to have so it pulls the exact same amount of charge for that same voltage? Okay. So, and the way to do that when they're in series is that the equivalent capacitance follows this reciprocal rule. Like that. So this is the rule when the capacitors, the pair of capacitors that we were talking about here, are in series. So that's that. The other sort of prototypical situation is when I attach the capacitors in parallel with one another. And this is a different situation. Notice how it's different here. The reason I've got the same V, this is C1 now, and this one out here is C2. Okay. So, if that's all true, then why these are in parallel, what makes them in parallel is the fact that the voltage difference across each capacitor is the same as the voltage of the battery. And it means that the equivalent capacitance, if we perform our analysis carefully, the equivalent capacitance for a series combination of capacitors is just the sum. So that's what we call the parallel combination, is like that. There. So that's how that works. You might be asking yourself, well, why would I ever want to do something like this? And it actually is practical. Let's say that you're designing a new, something that uses capacitors in it. It's a new rectification circuit or something like that. And you've decided, because of the voltage and the output that you need for your circuit, you need a very specific capacitance. I need 1.837 microfarads. Farad is the unit of capacitance. It's a coulomb per volt. Okay. I need that specific capacitance. Here's the thing. If you were to go to the internet and look up, I need I don't remember what capacitance I said, 1.838 microfarad capacitors, you probably wouldn't find it. That's pretty precise value. You probably wouldn't find it, because companies don't just say, well, I'm going to make every capacitance anyone could ever think of. They don't do it. Why would they? I mean, they'd have to build capacitors with new geometries all the time. What they do instead is they have a set of really specific capacitances that they print out that are sort of standardized. Now, there's a whole bunch of different ones. They'll do, let's do 1 microfarad and 2 microfarads and 5 microfarads and all that sort. So they make a bunch of different ones. I'll do picofarad ones and microfarads and millifarads and all these different ones. 2.7 and 9.8. But they'll do specific ones, and they'll be sort of these stock ones. But you don't need just any old thing. You need 1.838 microfarads. The thing is, you could take these really cheap, because that's what capacitors, any individual stock capacitor is really, really cheap, and you say, well, let's just take a bunch of stock capacitors and combine them in such a way, in series, parallel, mix, match, series, and parallel. 3 of them in parallel would work, plus add something in series to that, so that you get an equivalent capacitance which is equal to 1.838. So you see, you can make any capacitance you want by combining them in unusual and novel ways, so that you can get the exact capacitance you're looking at from the stock capacitances that you could get from any old electronics store. So that's one reason why you might want to do this. You say, well, I want a capacitance of 1.5 microfarads, but I only have 3 microfarad capacitors. Okay, well, how can you do that? Well, if you add 3 microfarad capacitors, you put them in series with one another, the equivalent is 1.5. Because 1 over 3 plus 1 over 3 is equal to 1 over 1.5. It turns out. So worked great that way. So I think that sort of maybe gives you a sense about how capacitors work. And we're going to be looking at resistors too. That's something we look at next week. So I'm going to ask if there are any questions now. Sammy said she doesn't have any more, but if this raised something, or if someone here wants to get in a question at the end, this is your time. If there are no further questions, I'm going to call it here. But I'm going to wait a little bit here to make sure that I'm not missing anybody's questions that wants to ask them. So I'll just pause here and wait for questions. If you don't have any more questions, just say no more questions. Goodbye for now, because then we'll see you next week. Okay, I'm not seeing any other questions pop up, so I guess I will end it here. I hope you found it useful. Again, sorry for the mix-up. I'll be a lot more careful next week with my schedule to make sure that we're not that I'm not putting up confusing or time conflicts, conflicting times or anything like that. So, again, thanks for your attention. I hope it was useful. We'll see you next week. Have a great rest of your week, and see you then. Stay safe out there.